All right, our next little piece is a couple of properties that series possess. And the first is this. So let's talk about properties of series. All right. And first we have a couple properties that are kind of standard. All right. We have the sum of C times A sub n. All right. And what this says is this: if you have the sum of a constant times the term, that's the same thing as the constant times the sum. What does this say? This says you can bring this constant out front. So if it's easier to move this constant out front, then what this says is you may. If you have a series where the constant is out front, if it's easier to have it back inside, this says you may also move in both directions. What this is something we should be familiar with. For infinite series, constant multipliers multiply along. Constant multipliers multiply along. You may factor out constant multipliers. All right? The second should also be very familiar. This is, now we know that if you have the sum of f plus g, the integral of the sum, we know the integral of the sum is the sum of the integral, right? The integral of the sum is the sum of the integral. Well, what this says is the sum of the sum. It sounds kind of weird, but it makes sense. The sum of the sum is the sum of the sum. The sum of the sum is the sum of the sums. And this is also true if you subtract. So the sum of the sum or difference is the sum or difference of the sum. It doesn't quite roll off the tongue quite as well, but it's the same notion. Now, this also, does not require, by the way, this does not require that this limit, the index begins at 1. So long as the index begins at the same number, it can start at 1 or 0. So this is also true for geometric, except each of these would start at n equals 0 rather than at n equals 1. All right? Now, there's one other little, let's leave that for the end here. So the next property is that, so the constant multipliers multiply along, and the sum of the sum is the sum of the sums. So we have that. Now, the next piece is this. If a series converges, then the terms go to 0. That is a true statement. That's a statement that we're not going to bother with proof for, but that's the property that series have. If the series converges, if the sum is finite, if you actually do get a sum, then the terms go to 0. Let's do a specific case. We know this. Let's go 2 times 1/4 to the end. This is a geometric series with r is equal to 1/4. That is less than 1. So this does converge. So this does converge. The series does converge. What this theorem says is, if you have verified that it does converge, then what will be the case is the terms, if you expand this out, 2 plus 2/4 plus 2/16 plus 2/64 plus 256 plus, and so on. The terms go to 0. What that means is each of these terms, you see, they're getting smaller. They're getting closer and closer and closer to 0. If the series converges, the terms go to 0. That is a true statement. If the series converges, the terms go to 0. So now, the problem is you might not have studied as much logic as was good for you, because now the question is, what if the series does not converge? What if the series does not converge. If you're not careful, you'll say, if the series does not converge, you might be tempted to conclude the terms don't go to zero. That is not the case. If the series does not converge, then anything could happen. All right? If it does converge, that guarantees they go to zero. However, if it does not converge, we don't know what's going on. It might or might not. Anything goes. It's the Wild West. Divergent series, essentially, anything could happen. All right? So, there is, however, if you've studied logic, this is called the contrapositive. There is something we can glean from this. And it says this: if terms do not go to zero. If the terms do not go to zero, then we may conclude diverges. All right? It actually is logically equivalent to this statement. If it does converge, therefore it goes to zero. If it doesn't go to zero, that means it doesn't converge. These are logically equivalent statements. For our purposes, really in the long run, and it might almost be best for you to forget this, because this is very easy to confuse if you're not real sure of the logic. This is what you want to hang your hat on. This is the key result. If the terms do not go to zero, that guarantees that it diverges. If the terms do not go to zero. If I take 2n squared, just expand that out. That's when n equals 1, this is 2. Plus when n equals 2, this is 2 times 4 is 8. When n equals 3, this is 2 times 9 is 18. Plus 50, plus, and so on. It is very clear these terms are not going to zero. If that's not clear, here it makes it even clearer. What is the limit as n goes to infinity of 2n squared? Well, that's 2 times infinity. That goes to infinity. These terms do not go to zero. These terms do not go to zero. Therefore, that series diverges. If the terms do not go to, if they do go to zero, then you can't gauge anything. But if they do not go to zero, if the terms do not go to zero, then we know the series diverges. So that's something we can set in concrete, and that will always be the case. In fact, this is called a test for divergence. If you just look at the terms and you know they don't go to zero, then the series clearly diverges. All right? Here, let's look at this. Let's take the sum as n goes from 1 to infinity of natural log of n. Well, what are the terms? Natural log of 1 plus natural log of 2 plus natural log of 3 plus natural log of 4. But look what's happening. Those terms are getting bigger. Natural log of 2 is bigger than that. Natural log of 3 is bigger than that, because we know natural log is an increasing function. Natural log of 1 is 0. Natural log of 2, natural log of 3, natural log of 4, natural log of 5. Those terms are getting larger and larger. They're not going to zero. These do not go to zero. Therefore, this series diverges. The end. So the series diverges. That's it. If the terms do not go to zero, that guarantees the series diverges. All right. There was one other little example I wanted to throw in at the end here. And I probably should have put this earlier in a video when we were talking about geometric, but I want to go ahead and insert it here because I don't want it to get left out in the cold. Consider the sum as n goes from 3 to infinity of, let's go just 1/2 to the nth power. This is a geometric series where a is 1 and r is 1/2. So this does converge, all right? However, this does not equal a over 1 minus r, because we're not starting at 0. That's why. we've left out n equals 0, left out n equals 1, we left out n equals 2. We've left out 3 terms. So this sum is not that sum. It is not the same thing as 1 over 1 minus a half, which is 1 over a half, which is 2. It is not that value. That is not the same thing because we didn't start at 0. So the question is, how do you find the sum? Well, you just break this down. What we do know is this. We know the sum starting at 0 is equal to the sum from 0 to 2 plus the sum from 3 to infinity. Right? This starts at 0, goes up to infinity. This starts at 0, goes up to 2. This picks up at 3 and goes off to infinity. This is the first, these are the 3 missing terms. Right? So we do know this is true. If you have a sum that does not, a geometric series that does not start at 0, you can find that because you can always express this equation. Now this, we do know how to find. We do know how to find because this does start at 0. This is a over 1 minus r. This is 1 over a half. This is 2. We do know this part is 2. And we know this because this is a finite sum. When n equals 0, this is 1. When n equals 1, this is 1 half. When n equals 2, this is 1/4. But that's all there are. Those are all the terms because we just have 0, 1, and 2. Right? And then this is what we don't know. This is, we don't know that. That's what we're looking for. But I can do that much algebra. This is 1 half plus 1 plus a half plus 4. So let's do that arithmetic. That's 4/4 plus 2/4 plus 1/4, 4, 5, 6, 7. That's 7/4. Let's just call this x. Subtract 7/4 across. Right? So we know that our value, x, or it's the sum, this is what we're looking for. That sum is given by 2 minus 7/4. What's that? 8/4 minus 7/4, that's 1/4. And so if you're trying to find this geometric series, if it does converge, if it doesn't converge, it doesn't matter anyway. But if it does converge, but you're not starting at 0, here's how you solve that little conundrum. You backfill the finite number of missing terms, find those explicitly, and then just do a little bit of algebra here. And that's how we can find the sum for a geometric series if it does not start at 0.